everybody. Welcome to today's CFA colloquium. I'm very happy that Kaitlin Kratter has come back to visit us. Many of us remember Kaitlin fondly, of course, from when she was an ITC postdoc here from 2010 to 2012, although it seems so much more recently. But anyway, Kaitlin, I could summarize her research by basically saying if it's like a disk, and it could make planets or stars or break apart, Kaitlin would like to figure out why and how. Okay, that's pretty much my simplest summary of Caitlin's research. And the reason I have to give such an overall summary is because she's worked on many different forms of that problem. And today, I think she's only going to talk about 3 of them. But before I let her start, I should tell you that she's written a really wonderful annual reviews article very recently called Gravitational Instabilities in Circumstellar Disks, which is a more eloquent way to say what I just said. And that she went to Barnard undergraduate. And I first met you when you were in Toronto with Chris Matzner. And then she's worked with lots of other people in addition to Chris, even when she was a graduate student. And you won the Plaskett Prize, didn't you? Yeah, she won the prize for the best thesis in Canada, essentially. And then she was an ITC postdoc here. And then she went to Gila as a Hubble Fellow. And then she went to Arizona, where she's now on the faculty, doing wonderful things that she's about to tell us about. So thank you very much, Kaitlin.
All right, Alyssa, thank you for that wonderful introduction. How's the volume? I'm okay. I'm not screaming at you too much. They promised me they would turn it down up there if I was screaming, because I get really excited. So as Alyssa said, I'm going to talk to you about a few different problems today, and I will make a disclaimer up front that while I hope to have a cheerful demeanor, I'm kind of going to be a little bit of a downer today, in the sense that when I say 3 puzzles, I kind of mean I'm going to talk about 3 things where we found some problems, but we haven't quite got the solution yet. So you can think of this as an inspiration for some of the students to, do better than we have done and come up with some answers. And so maybe in a couple of years, I can come back again and tell you about 3 answers to long-standing puzzles in star and planet formation. So the 3 things I want to focus on today are represented by these images, and while this is going to be a theoretical talk, I will try to keep you entertained with some nice pictures along the way. I'm going to start out and spend a fair bit of time talking about the puzzle of close binary formation. I alluded to this a little bit in my ITC lunch talk, but I'll talk about what we do know about binary formation and where we have some really open questions. I'll then move on to talk a little bit about planet-disk interaction, and in particular I'm going to focus on the puzzle that is these asymmetric features that we keep finding in protostellar disks. It seems every time we upgrade our resolution abilities with ALMA, we find more and more things that look messy and not like nice, smooth power laws or exponentials. In the last part of my talk, I'm going to focus on a local binary analog that is the Pluto-Charon system. Hopefully you've had a chance to talk to your local expert here on this, Scott Kenyon. He's working on solving some of the problems which I haven't been able to. So come back again in a couple years and he can tell you the answers. Okay, so the first part, binary formation. So why should you care about binary formation? I'd say there are many, many reasons. The first of which, it keeps being relevant to say this, is LIGO, right? So LIGO keeps finding these massive black hole binaries. And for some fraction of the theory community, their existence has been a puzzle. But what this should really indicate to you is that models of close binary formation are poorly understood across the entire stellar mass range. If we want to understand the origin of these systems and of the neutron star binaries that LIGO was built to find, if they exist, we need to understand binary formation globally. If you don't care about gravitational waves in LIGO and you just care about the numbers, well, 50% of solar-type stars are in binary systems, and it's more for higher mass stars. Now, I know Charlie might tell you, well, everything's an M-dwarf, maybe we shouldn't care, but I still think the rest of the stellar mass function is interesting. This is a really nice plot from a great summary paper of binary statistics that was written by a former graduate student here, Max Moe and Rosanne DeStefano, that just came out this year. If you want to know anything about binaries, this is really the best resource on it by far. And what they're showing here is that as a function of primary mass, the multiplicity for mass ratios above 0.1 is just this strong climbing function of mass. When this number gets above 1, what that means is, on average, a star will have more than one companion. And so during the rest of this talk, I will be talking about both binaries and, in many cases, triple star systems, where there's a whole lot more fun things that can happen. If you're a planet person, of course, binaries impact planet formation. The fact that binaries are not an unusual feature for stars that host planets means that you can't just throw them out of your planet formation models. And if there are any explosion types in the audience, of course, type 1a supernova rates are a strong function of our understanding of binary stellar evolution, and that's something else that this great guy, Max Moe, has been working on. So keep an eye out for some really fantastic papers from him. Okay, so what do we know about binary formation? Here's where I'm going to argue that we've actually done a pretty good job and solved some things. So I would argue that there are two dominant modes of, and I will admit here, wide binary formation: filament or core fragmentation and disk fragmentation. So the idea behind filament or core fragmentation is that on very large scales within the giant molecular cloud, you have these turbulent structures, and sometimes on a scale of 1,000 or maybe 10,000 AU, instead of getting just one overdensity, you get two overdensities, maybe even 3 or 4, that are relatively close together. They're still gravitationally bound, and they will in-spiral to form a relatively wide binary. That's what's illustrated in these cartoons over here. And the second mode is this idea of disk fragmentation, which seems to work better for higher mass stars. And in this case, we just have to be a little bit more patient. We wait for one star to form first, and in some cases, if the infall rates onto that protostellar disk are sufficiently high, you can build up enough mass in that protostellar disk to become gravitationally unstable and form a secondary mass. And because of the scales that are involved, the mass in the disk, the temperatures in the disk, and the infall from the background cloud, these objects tend to form stellar mass, or at least brown dwarf mass objects, not planets. So this is a really good way, we think, to make massive stellar binaries. And Anna Rosen, who's a new arrival here to the ITC, has done some nice work on these disks as well. So you should talk to her about that. So lest you think I am just a, hopeful theorist, what I think has been really exciting in the last couple years is that we actually have observational evidence for some of these things. So this is a really beautiful result that came out in Nature a couple years ago with Jaime Pineda and Stella Offner, two others who have CFA backgrounds, where they used JVLA observations to find a gravitationally bound young quadruple system in the Perseus molecular cloud. And so the structures that we see and the masses that we see and the separations that we see are all really consistent with this picture of large-scale fragmentation into a multiple system. Now, I thought this was great, but I was admittedly even more excited when just last year, John Tobin and I and a whole bunch of other collaborators saw this amazing image in our data set. And I don't know, maybe it's because I'm really close. It doesn't look, it looks pretty good up here. So I saw this and I just fell off my chair. This to me looks like the smoking gun of a fragmenting, gravitationally unstable disk where you have two relatively massive objects in here. These each have a dynamically estimated mass of about a 1/2 to 1 solar mass. You've got this maybe 1 or 2 arm spiral structure, and then this bright blob out here, which looks like it's dominating the mass budget, is really just big, is just bright because it is colder and more diffuse and probably a recently born fragment. I can help your eye if you want to see the theorist's picture of this. Let me rotate it for you. Now you can see that we, predicted exactly this structure, 6 years before its detection. Now this was from a set of very simplified models, so there's no reason to expect this kind of morphological agreement other than the general statement that when you get this instability, you tend to form these kind of systems relatively frequently. I don't know what happened to this guy in the image. He got lost somehow. So To be fair, we've done better than just, comparing pretty pictures. We actually made a relatively simple one-dimensional model that showed that if we do our best estimate at what the surface density profile and the temperature profile and the rotation profile is in this disk, it does in fact agree with simple models for gravitational instability. What I'm showing here is just the radius in the disk, and this is an azimuthal average, which if you looked at that previous image, you might be somewhat skeptical of. And then each of these curves represent sort of standard quantities you might want to calculate, the 2^3 parameter, the surface density, or the temperature, or how quickly it cools. And again, all of them basically give you the same result, that we should expect this disk to be unstable, fragmenting, and making massive objects. This is just one of the moment maps that shows you the rotation, where you can clearly see that the center of mass is around these two objects here, and this bright thing really is a low mass object. So those are two sort of case studies where we now can say wide binary formation seems to happen, disk fragmentation seems to happen, but we have some other population-wide evidence as well that there might be these two modes. The first one, I will emphasize that I have underlined and starred this word hint. So before the observers get all up in arms about these error bars, this is not conclusive, but I think it's kind of interesting to see that if we look at very young class 0 and class 1 objects at higher resolution than had done before, this is again work led by John Tobin, that we can resolve binaries, and we see a bunch of binaries on these scales of 10,000 AU and down to 1,000 AU, and then we see this other little bin pop up right around 100 AU, where we might expect to see disk fragmentation. And there appears to be a deficit in between in the very youngest sources. Now, again, the error bars are big, the numbers are small. Time will tell if this trend bears itself out, but I think it's an interesting demonstration that at the very early times where you would expect to see this imprint of small scale and large scale, maybe it's there. There's more evidence, though, that I think is somewhat more conclusive coming at later times, and this is again from this really nice work by Max Moe and Roseanne, where when they have done a careful job looking at binary statistics and going beyond just how many stars have binaries as a function of mass, but trying to understand how does the mass ratio distribution scale with separation, how does the mass ratio distribution depend on primary mass, they found something really interesting. So if we just look at this bottom panel here, what this slope is telling you is about the mass ratio distribution of different type stars as a function of separation. And what this line down here shows you, minus 2.35, is the mass ratio distribution you would expect for binary stars if it was by random pairing from the IMF. So if I make binaries by just drawing two stars from my IMF bag and throwing them together, this should be here the whole time. Instead, what we see is that at closer separations, the slope is very, very different from that. It's much closer to a uniform distribution in mass. And at very large separations, we start to approach this random pairing from the IMF. This is exactly what we would expect from these two different modes joining together. That at small scales, where the objects are maybe sharing a mass reservoir in a disk, we should expect that the star knows about its companion's mass because they can share material. When we go to these very large separations, where things are just forming from two random turbulent fluctuations in the same filamentary structure, we shouldn't expect the process to be substantially different than single star formation drawing from the IMF. So again, this is not conclusive. We certainly don't see two peaks. Solar type stars seem to behave a little bit differently from all the rest of the stars in the sample. There's a lot of mystery still here, but I think it's starting to push towards an answer. Okay, so now here's where the problem comes in. I just told you a nice story about how great, I think we've solved binary formation, but of course I was only talking about wide binary formation. This core fragmentation picture maybe works on scales of thousands to 10,000 AU. Disk fragmentation is hard-pressed to go to scales much less than 30 AU, more like 100 AU scales. And then there are these guys, which are admittedly rare, maybe only 2% of the overall binary population for solar-type stars. But they're on a very, very different scale, orders of magnitude smaller. And we need to find a way to take these primordial fragmentation models and get things all the way down to these very close separations where they can then go on to seed all sorts of interesting astrophysical phenomena. So you could think of maybe a handful of ways that you might make these. So maybe I've just lied to you and ignored the in situ formation mechanism. We could have a hydrodynamic migration picture, or maybe a dynamic migration picture. And what I would argue to you is that the in situ picture is pretty well ruled out at this point. One easy way to understand that is that if you calculate the contraction of the initial protostar, a la Larson 1969, you all maybe remember from a star formation class that there's that phase where you form that first hydrostatic core. Well, a lot of these binaries live inside that first hydrostatic core. So it's pretty hard to figure out how you could get fragmentation inside that structure. And there's been a lot of work on this over the years to suggest that it's really unlikely. For hydrodynamic migration, you could imagine a couple different ways to do this. You could either imagine that you have two stars in the same disk that are interacting and exchanging energy and angular momentum with the gas and migrating inwards. Or you could imagine you have two separate disks, each with their own host star, that also interact and somehow dissipate energy and angular momentum. And I'll talk a little bit about both of those in a minute. And then finally, dynamic migration, what I mean here are things that don't involve gas. So things that can involve either violent instabilities between three or more stars, or perhaps something that's a little bit more long time scale, like a Kozai-Lidov oscillation, where eccentricity, excitation plus tides can bring things in to very, very close separations. So let's look at each of these pictures in a little bit more detail. So we've done a fair bit of work now on looking at how either disk-disk interactions might evolve binary orbits. This is also work that was led by a former CFA graduate student, Diego Munoz, or how binaries can evolve due to interactions with their external circumbinary disk. And while there's a lot more work to be done on this, the short answer is that it's very difficult to remove quite enough energy and angular momentum just by interaction with the disk, because the disk is a finite mass and angular momentum reservoir. One of the more popular models is this dynamical model of Kozai-Lidov oscillations plus tides. And you've probably had colloquia about this before, so I'm not going to go into the details of how this mechanism works, but the basic picture is you have a triple star system that is hierarchical. Under certain conditions, for sufficiently high relative inclinations between the orbits, the eccentricity of the inner orbit can get excited, and then if it gets excited to have a small enough pericenter, tides can begin to circularize the orbit and bring in the star to periods of only a few days. And this has been, for the last decade or so, the standard model for how we make close binaries. And it's a very, very compelling model. There was this really nice paper by Dan Fabricki and Scott Tremaine in 2007 where they showed that if you started with this initial distribution of inner binaries and they picked sensible distributions for the tertiary companion in each of these cases, that they could shift these wide binaries, quote, wide binaries from periods of, tens to hundreds of days down into this peak where tidal circularization has created these very short orbits. Now, the problem with this is that their initial distribution kind of cheated in the sense that they already made a lot of close binaries. So if I draw where those other two mechanisms I talked about operate, they're all the way out here off the edge of the plot. This is where we think the binaries start. So starting with a bunch of objects filling in here, it's not clear we've solved the whole problem. We have to make this subpopulation before we can do this step. There's another problem that only became, I think, apparent very recently, and that's a timescale problem. So in previous models, because this Kozai-Lidov oscillation is a secular timescale instability where it means that you have to wait many, many orbits to excite eccentricities and then many, many orbits for tidal circularization to happen, we expect this process to take gigayears. And most previous models allowed their simulations to run for gigayears. But here again, Max Moe and Roseanne came to the rescue, because when they went back and they did a really careful analysis of the close binary fraction, they found that by 5 million years, all the close binaries were basically there. At least 50% of the close binaries already exist after 5 million years. So if your close binary formation method takes a gigayear, think you're out of luck. The fact that we have circumbinary planets also is a hint, because we know that planet-forming disks only live for a few million years. So if you have a 10-day orbit and you've got a disk that forms planets around it, you had to get those binaries onto that 10-day orbit within about a million years. Now there's some good news here, and this is what Max and I have been looking at in this recent paper. First of all, if you try to make young stars undergo Kozai-Litov oscillations and have very high eccentricity orbits with very short pericenters, you get a little bit of a bonus for two reasons. One, pre-main sequence stars are big. They have radii of several stellar radii. So you get a boost in how efficient your tides are. Secondly, if you start out with your binaries on wide orbits all the way out here, then the only systems that can undergo tidal circularization are ones which reach eccentricities of like 0.99. And what that means is that the standard tidal models that people use, the so-called equilibrium tide models, are a little iffy. Because as you will remember, right, tidal forces scale very strongly with separation. So almost all of the tidal evolution happens at pericenter, and almost nothing happens the rest of the orbit. And so what we think might be a better model in this case is something called a dynamical tide, which is basically like stellar capture. So if you remember the old models of taking two stars that are unbound and throwing them at each other, and occasionally they would get captured, that's kind of the picture you might want to have in your head for the formation of close binaries on the pre-main sequence. So what this plot here is showing is that in the standard model, it takes gigayears to undergo these eccentricity oscillations that eventually lead to tidal circularization. If you start out with an extremely eccentric system with big stellar radii, and you use this dynamical tide model, you can get very, very rapid shrinkage within less than a megayear. Now, for the experts in the room, you might be thinking, gosh, it seems like a bad idea to combine dynamical models with secular models. You're probably right. I don't know how to do it any better, and so this is something that needs a little bit more work. But nevertheless, we think that there's something interesting and worth exploring here. So what about that other dynamical model? This seems to be maybe somewhat promising. We should also consider the instability model. And now again, I'm going back to a movie that I made when I was a postdoc here because I think it's a nice illustration of what instability looks like. So these are just three stars that have gotten too close together and their orbits are unstable. You can see they undergo many close encounters. And you might think, well, this solves the problem. I can just take wide triple systems, kick one guy out, and make a nice close binary. If you take the time to do a simple order of magnitude calculation, of course, what you will find is that as messy and violent as that looked, to go from the typical separations we think we start out at, down to these 10-day orbital periods, you need to remove basically 99% of the orbital energy. And if you take typical mass ratio distributions and you take three stars and you kick one guy out, you remove about half of the energy. And that's simply not enough. So it's very difficult on its own for this kind of mechanism to create a bunch of close binaries if everything starts out wide. And so we think maybe what you need is a combination. And so what I'm showing here is a plot from our paper showing where we started to do a series of sort of population calculations where we said, okay, what if I start out with reasonable initial conditions based on formation models and then try to make some close binaries? So this is period in days. This is the companion frequency per log p. This is the overall expected distribution you should get out at the end of the day. We're interested in this 2% close binary fraction with periods less than 10 days. And we say, okay, we can imagine starting out with populations that look like this for the inner companion in the binary and then the outer companion, assuming that, say, these maybe form in disks and these form in cores. And when we evolve all of these models and consider both Kozai-Litov oscillations plus dynamical tides, when we consider what happens for systems that begin on dynamically unstable orbits, we can't quite fit the data. We can't quite make enough close binaries. So here again, you see the initial distributions for the triples. You can see in red and blue the systems that were progenitors over here and the final systems over here. So red systems here show the inner progenitor and the outer progenitor that make this distribution over here in 5 million years. And the blue line shows you what you get after 5 gigayears of evolution. And of course, what we need to get to up here is about 2%. So evolving for longer times helps you a little bit, but at the end of the day, we're only recovering maybe half of the close binaries from this combination of models. And so our conclusions are that we probably need a combination of migration mechanisms. So we need to somehow figure out how these kind of hydrodynamic mechanisms can operate in concert with these dynamical mechanisms to give us the full complement of binary systems that we need. And this is, like I said, still kind of an unsolved problem. We're going to need to do a lot more work to figure out exactly how much of the process we can accomplish at this stage to see what we get as our initial conditions for cosi and dynamical instability. So this is ongoing work. I'll say that I expect we'll have some very good data to help us in the coming years, because Gaia is going to give us an unprecedentedly large sample of perfect constrained orbits for a whole bunch of triple systems in the early to mid 2020s. So we'll have an answer, but we may have to wait another 5 years. Okay, I'm going to move on now to another puzzle, which I alluded to at the beginning, and that's disk asymmetries. So this is a beautiful compilation of ALMA data from Ninka van der Merel, published in 2016. And you see just this array of interesting features. I mean, we've really come a long way in our observations of disks. And now you can basically find any kind of shape you might imagine. What I want to focus on are these very lopsided images here, where it looks like we have a whole bunch of flux coming out on one side of the disk and nothing coming out on the other. So there's been a popular explanation for these systems, which is the Rossby Wave Instability. So for the hydrodynamicists in the room, you can trigger the Rossby Wave Instability when you have an extremum in your inverse vortensity. Vortensity is just vorticity divided by density. So that's the formal definition. If you are imagining that you're having this instability arise in a Keplerian protostellar disk, what you need is a density bump. That's a little bit easier to think about. So if you have a very sharp density bump in your nice, smooth Keplerian disk, you can generate this instability. And what this instability does is it causes the gap edge to start to break up, and I'll show you a movie of this in a second, and you get these vortices that merge into this one big honkin' lopsided picture that is a single m=1 vortex. So here's what it looks like. These are simulations run in the 2D hydrodynamics code Fargo. These snapshots are taken once per orbit. How do you get that density bump that we need? You put in a planet. This is a very popular thing to do, again, in disks, right? If you see a structure in a disk, gee, wouldn't it be fun if it told you there was a planet there? This is the game we all like to play. And you can see it does a very nice job of creating that asymmetry that is now orbiting with the outer disk edge. It's nice and bright. This looks great, right? We have explained this nice, crazy-looking feature, and it means that every time we see an asymmetry, we've got a 5 Jupiter mass planet. That would be fantastic, right? Lots of fun. Everyone likes planets. Okay. As I told you at the outset, I'm not here to be a cheerleader. There's a problem. I'm going to show you the same movie, but now I've done something different. I've taken into account the fact that if I want to make a Jupiter or a 5 Jupiter mass planet, that takes time, right? They don't form instantaneously. In fact, they take thousands or tens of thousands or millions of orbits to form. So here's what happens if I do that. Now we're moving through time a little bit faster. You can see that the instability is still generated, but it looks very, very different now. I should point out, sorry, I forgot to mention, this is the dust on the right. So we've done gas and dust simulations as well. And so what you're seeing here are dust grains that are gathering in these traps. And of course, what you're observing with ALMA is the dust. I'll talk a little bit more about this in a second. So what you see here, though, is in this case where we've allowed the planet to grow at a more realistic, albeit still pretty fast rate, because there are some computational limitations here, you get something that looks very, very different at the end of the day. It's elongated, it occupies more than half the disk, It just doesn't have that same characteristic that we saw in some of those early images. And again, we think this is probably the more realistic case. So you can see again here, this is the dust on the right, and it's occupying more than half of the axis, and it's in this very confined region. Okay, so fast growth, which is what we saw we needed in that first picture, is really fundamentally inconsistent with vortex formation in the first place. So, maybe it doesn't seem like a crazy thing to say, oh, well, of course it takes planets a little while to form. They don't form instantly. But it's even worse than that, because there's another requirement for this instability to arise. And that's that the disk has to have a very low effective viscosity, or in other words, it needs to have very little turbulence, be very, very laminar. And the reason for that is that in order to trigger the instability in the first place, you need that density to be really, really steep, right? You need it to be really sharp. And effective viscosities, turbulence, what does that do? It smooths things out. So to have the right initial conditions in the first place, I need low turbulence, low viscosity, nice smooth laminar flow. Well, if we take that limit for the disk, we can calculate in at least a simple steady state accretion model what the mass flux rate is through that disk. And the less turbulent I make my disk, the slower I expect it to accrete. So if I calculate the accretion rate I would expect in a disk that has low enough turbulence or viscosity to allow the instability to rise in the first place, I find that it should take me 1 million orbits to grow a Jupiter-mass planet. So the simulations I'm going to show you now, we don't approach 1 million orbits because we can't run a simulation for that long. But the trend isn't good. So what we're showing here is growth time in planet orbits versus the lifetime of the vortex, also measured in planet orbits. Up here on the top, I'm showing that for different distances measured in a U, where a growth time of 10 to the 5 years corresponds, just to give you some reference. So it depends obviously on the orbit, on the semi-major axis, because that's how you convert between orbital periods and physical timescales. What you can see is that for different effective viscosities and different mass cases, as you approach longer growth times, the vortex gets weaker and the lifetime declines precipitously. The reason there aren't a full sampling of points here isn't because we had limited computational resources. In fact, it's because when you go to much longer growth times, especially for this case, the vortex never forms at all. And again, when it does, it is weaker and has a very, very different character. So this is showing it to you in the gas. I showed you the movies before. I just want to emphasize that when we do simulations now, we can't just look at the gas. We have to look at the dust. And dust doesn't behave identically to gas because it's a pressureless fluid. So in these simulations, we've now gone back and we've put in dust. This is with a code written by Xiaohan Zhu. And so you put in a secondary fluid which doesn't experience pressure. We include gas drag because, of course, the gas rotates at a slightly sub-Keplerian velocity because there's a pressure gradient which counteracts the force of gravity. And so dust particles move at the Keplerian velocity, or they try to. So there's this headwind, and that causes them to experience a drag force, and that changes how they move in the disk. And we also include a diffusion term. And so if we take these models for how the dust behaves, and we run them at a wide range of wavelengths, we can then convolve them with the ALMA beam to see what these simulations would actually look like. And on the left side, I'm showing you one of the vortices that we would expect for these quickly growing, unrealistic planets. And on the right side, I'm showing you what we would expect for these slowly growing planets, still in the optimistic case where it only took 1,000 orbits to grow, which is still probably too short anyway. And what you can see is that the picture is very different. So this is just a warning for, if you want to fit one of these very concentrated asymmetries with some planet model, it really matters how the planet grows in the disk, because it strongly affects the type of instability that you trigger. So I'm not yet convinced that even these are realistic explanations. I have nevertheless put on the other on this slide 2 examples that might be more consistent with this slowly growing planet case, these things that occupy more than 50% of the disk azimuth. But I'll just conclude this part of the talk by saying that I think we have to be cautious when we use these numerical models to try to reproduce the simulations. First of all, because numerical constraints push us to considering kind of crazy unphysical things like Jupiters that grow in 10 orbits. Again, you can think of this as taking your nice smooth disk, taking a hammer and whacking it, right? It shouldn't be a big surprise that you get an answer that's a little bit funny. For some of the numerical experts in the room, I'll tell you the problem is a little bit worse than that. It's not just that you might worry that that's a little unphysical. There are also other very strange things that happen. So if you change the gravitational softening length in your disk in one of these fast-growing cases, the lifetime of the vortex changes by a factor of 7. It doesn't change monotonically as you go from one side of the softening length to the other if you pick some fixed value. So there's all sorts of funny things that arise when you basically hammer your disk with a rapidly growing planet. I should also point out that you might be concerned about these simulations because they're isothermal. We don't include this accretional heating that the planet might generate. So this might counteract some of the effects that we found and increase the amplitude of that density bump for a slowly growing planet. So it's worth considering in future models how that might change things. But nevertheless, I will just end by this part of the talk by saying we need to be very cautious in interpreting these asymmetries. I'm not convinced we have a good answer yet. Okay, so that's the second part of my talk, and now, to be totally schizophrenic, let's jump back into the solar system and talk about the Pluto-Charon system. I sort of call this part of the talk an excuse to show New Horizons data because I think it's absolutely phenomenal. I was really excited when this started to come out. I think this has just been really, really amazing. There's been some fantastic work. We got to write a paper with the word cryovolcanism in it. I thought that was pretty fun. But let me just remind you of some of the reasons why this mission was phenomenal. I think in this day and age, sometimes we can get complacent about space missions and space travel. So I just thought I'd like to show the sort of trajectory of New Horizons as it passed by the Pluto-Charon system. So here's Pluto and Charon. As you might recall, it has 4 circumbinary moons, Styx, Kerberos, Nix, and Hydra. And they have periods of, 6 days for Charon, Styx is 20, Nix is 24, Kerberos is 32, Hydra is 38. And New Horizons traveled after 7 years of going through the solar system in between all of these objects. They sort of threaded this needle. And they had all these, practices to sort of make sure they could adjust their trajectories at the last minute. And they told me that it was, within a few seconds of their predicted arrival times at each of these different places. So it's a really phenomenal engineering task, I think. Just really, really cool stuff. And obviously the images that have come back are amazing. But let's talk a little bit about sort of the physics of this system. So this is looking at it face on. This is a pre-New Horizons image with HST, where you can again see Pluto and Charon, and then the 4 circumbinary moons. Now, if you want to understand how these things form, again, you should really talk to Scott here, because he's done some of the most sophisticated work on this to date. It's been a real long-standing problem. What we do think we understand is how the inner big binary formed itself. We think that the origin of that binary is a giant impact scenario not so dissimilar from the Earth-Moon system. We think that 2 partially differentiated bodies smashed into each other, and the remnant of that created Charon. One of the neat things about it is that this model predicts that the material that gets sloughed off after this collision should be pretty icy. And if we think the moons formed out of that remnant material, they should also be icy. And actually, when I was at the CFA, we wrote a paper that suggested that the masses of those moons were consistent with icy albedos, and both follow-up work with HST and New Horizons has actually confirmed that our dynamical mass predictions for these things were right. That doesn't mean we've explained how they formed, but we at least think we know what they are. So we think that the binary itself formed this way, initially on a much closer orbit than it is today, probably eccentric from the collision, and then it tidally evolved outwards to become tidally locked on a 6-day, almost perfectly circular orbit to the best of our ability to measure it. So why is this a problem? Why is it hard to form these moons out of that remnant material? So if we look at where the moons are today, we run into this problem of basic stability. Now, for those of you who were at my ITC lunch talk, you might remember I talked about one of the fun things about planets in binary systems is that you take a binary and you try to put a planet around it. If you put it too close, that time-dependent potential, those strong kicks, will ultimately make the planet leave the system. You can't make a nice, stable Keplerian orbit if you put the planet too close to the binary. What does too close mean? Somewhere between the 3-to-1 and the 4-to-1 period ratio with the binary. So, because Charon and Pluto had their orbit evolve and started out much more eccentric, we can ask, where were orbits stable around the binary in the past? So on the x-axis here we have time in years. This black line shows Charon's evolving semi-major axis, and this shows its evolving outer radius for different eccentricity models. So most of the collisional models suggest that for different orbital eccentricities, it had excursions out to, this is in units of 10 to the 3 kilometers, so 40 or 50 times 10 to the 3 kilometers. So this is the evolution, and that's the black line down here, and what these colored curves are showing is where the stability boundary would have been for Styx, Nix, Kerberos, and Hydra. And so the fact that these blue lines cross these pink lines show that for most of the eccentric evolution models for Charon, all of the moons except for maybe Hydra at some point should have been driven unstable by the tidal evolution of the Pluto-Charon system. So it's very difficult to see how they could form where they are today or even closer in without being destabilized by the eccentric orbital evolution of the inner system. So again, talk to Scott, who's trying to figure out how to solve this part of the problem. I'm going to do something a little bit easier. I'm going to start from the hypothesis that, okay, we had this collision, it threw off some material, it landed in a debris disk, and then we can do the simple thing of modeling how that disk of debris evolved while Pluto-Charon evolved. I'm not going to try to form these exact moons. I'm just going to ask a simpler question, which is, where should this debris have gone, both in the Pluto-Charon system and in the rest of the solar system? So what we think, based on some simple physical calculations, is that most of the material should be ejected. Some of it will just go unstable by coming too close to the binary. Some of it might collide with one of the two objects, but we think that should be a small fraction. Now, just because it's a small fraction doesn't mean it's uninteresting. And again, we can show with some very simple physics that very little of it will collide with Pluto because it's the more massive body in the system, but some of it should collide with Charon. Now, the reason this is interesting is that what do we do with bodies in the solar system that have craters, right? We count them. Exactly. You count them and you measure them, and then what do you do with those numbers? Ages, right? So people have done that. The other thing you do is you infer something about the population of stuff that hit it, right? And so what you may not be familiar with was one of the big goals of New Horizons was to look at the surfaces of Pluto and Charon, which were thought to be 4 gigayears old. They were thought to be totally inactive, dead bodies. Okay, we knew that there was atmospheres, but they were thought to be pretty inactive and dead. And then we were just going to go count the craters, measure their sizes, and back out the size distribution of the Kuiper Belt. And that's really cool, right? If you learn about the size distribution of the Kuiper Belt, you learn about the most primordial bodies in the solar system. You can say something about planet formation, about planetesimal formation. So that's great. But if you had this disk of material that's contaminating your signal, you might have a problem. So we wanted to ask, how contaminated should that signal be? So we ran a series of simulations for different Pluto-Charon evolution models where we just tracked the evolution of the debris. So you can see here a face-on picture of the system, where these are, again, all test particles. They're not interacting with each other, and they don't have any mass. But what we can do at a later time is go back and convolve this model with any distribution for the debris that you like. This is the edge-on projection here, where you can see that the objects are being scattered out to large radius. If we zoom out even more to the Hill radius, we can see many of the bodies being ejected into the solar system. This is a histogram showing where the bodies are being lost from as a function of distance from the center of mass of the Pluto-Charon binary. These pink lines indicate the locations of the current moons in the system. So it's not obvious, for example, that there's a huge amount of stuff at them. It turns out that all of the moons live very near mean motion resonances with the Pluto-Charon binary. So they're basically in this almost resonant chain of 4 to 1, 5 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1. Got that right? Yeah. And of course, none of them are actually in the resonance, which is another puzzle that nobody has totally figured out yet. But you can see over the course of the simulation, we start to carve some interesting structures in the disk. And again, we haven't tried to make the actual moons yet. We're just trying to see where the stuff goes. So what can we learn from studying these collisions and ejections? So for a given debris size distribution, we can predict, again, the number of craters that have a disk origin, which allows us to constrain what else might be coming from the Kuiper Belt. And we can also look at these bodies that were ejected, which was the majority of them, and see whether or not they stay in the solar system. So first, let's look at the things that collide as a function of disk properties. So on the y-axis here, we have the particle size distribution. That's the index Q. On the x-axis, we have the disk surface density distribution. For reference, for protoplanetary disks, you expect, say, this kind of surface density distribution. For the protolunar disk, the model is for something a little bit steeper. And the nominal expectation for the Kuiper Belt would be right here. And so what the 2D histogram underneath shows is how many colliders we would expect with a radius bigger than 300 meters. The reason we've chosen 300 meters is because that's what we expect to create craters large enough to be observable by New Horizons on the surface. That calculation is non-trivial because it depends a little bit on the surface properties of the thing that you're hitting. So you need to know kind of the properties of really cold ice in the outer solar system to get this right. And so you can see that depending on exactly the type of properties with the disk, these two different panels show you what happens when you allow Charon to migrate outwards. And this is when you put it at basically its its current separation, but with a little bit of eccentricity. You get anywhere from a few tens to a few 100,000 objects that might collide with the disk. We expect for reasonable parameters that the number is maybe something around hundreds to thousands of craters in principle could have been produced on the surface from this debris disk. What about those ejected bodies? So this is showing the solar system scale of the picture, where we have semi-major axis in the solar system on the x-axis, and for each of these different subpanels, we have cases where we have taken the Pluto-Charon system, taken the bodies that we know are lost from it, and we've injected them at different points. We say, okay, I know where things are when they leave the Hill radius of Pluto-Charon. Now I'm going to take the Pluto system, pop it into the outer solar system, including Jupiter and Uranus and Neptune. I can include the migration of Neptune outwards, which we think sweeps Pluto and the rest of the resonant Kuiper Belt objects outward with it. And I can ask, where does this stuff go? Does it get ejected from the solar system? Does it collide with Jupiter? And the answer is yes, both of those things happen. But the more interesting thing that happens is that it gets caught, as you might expect, in mean motion resonances with Neptune, just like Pluto itself. Because when things get ejected from the Hill radius of the Pluto-Charon system, the velocities are relatively low compared to the orbital velocity of the Pluto-Charon system, and so it has similar dynamical features to the Pluto-Charon system itself. On the left side, I'm showing the case where we aligned the ejections So the disk of the debris disk with the Pluto-Charon heliocentric orbit, and this is the case where it's misaligned. You may know that the entire system is actually kind of tilted on its side at almost 90 degrees to its own orbit. Also funny, no, I'm not sure there's a really great explanation for that yet either. But in both cases, you see that many of these objects are trapped in the mean Roche resonances. And the ones that I'm particularly interested in are these ones that are in the 3-2 along with Pluto. And what this pink color bar here is showing you is that the ratio of the ejection velocity to the escape velocity, and the fact that these are all the same color tells you that they have low relative velocities with the Pluto-Charon system. Why should you care? This means that we might have a collisional family, kind of like Haumea. Now, these are probably small bodies. It's not clear how small, but what this suggests is that if you had a massive disk of material that formed as part of the Pluto-Charon forming impact, there should be evidence of it trapped in the 3-2 along with Pluto, that if you have a big enough telescope or something in space and somebody's willing to give you the time to look for it, there might well be a collisional family of other objects. And what this could do is give us more constraints on the properties of that disk. If we could look at the distribution of albedos, the distribution of sizes, we might get some more hints as to how the Pluto-Charon system formed. So I'll wrap up this part by just saying that the conclusions that we've reached are that even though there's a possibility that some small number of craters on Charon's surface could have arisen from this debris disk, so far we haven't really found any. So the crater countering experts have gone and looked at the surfaces, and as you may know from news articles on the New Horizons system, there was another issue with the two bodies, which is that their surfaces were not really primordial. There was lots of evidence of some geologic activity, less so on Charon than on Pluto. But when they looked, they haven't found a bunch of small craters. This is really cool for Kuiper Belt object models because it tells us that we think that the initial population of planetesimals was big, and it also maybe tells us that there was an upper limit on the amount of mass in this primordial Pluto-Charon disk that could have contributed to a population of as yet undetected small craters. I also mentioned that I think we might be able to find a Pluto-Charon collisional family from this ejecta. This has not yet begun. I think LSST might be able to do it. I think it's going to be a little bit tricky depending on the observing cadence, so maybe we have to wait for JWST or maybe even GMT. I'm not sure. So I will finish up with a little bit more gratuitous advertising. So I want to point out that we're organizing another conference on star and planet formation in Arizona this March. We had one in 2015. It was a lot of fun. It's going to be at the Biosphere 2 Center. Yes, that Biosphere, not the Biodome. That was the bad Pauly Shore movie. But it's a really cool venue for conferences. It's a small group. We strongly encourage submissions from graduate students and postdocs. We have subsidized the registration fees. Everybody stays together in houses. It's great. As you can see from the background slides, Arizona is beautiful that time of year. It is cold and miserable in Boston. I lived here. I know. Don't try to tell me otherwise. So come out and see some nice wildflowers and water and greenery. And then lastly, I'll just say we are also having a Steward Theory Prize Fellowship postdoc this year. So if you have excellent graduate students, or you are an excellent graduate student or postdoc, and you're interested in coming to Arizona, we have theorists working on all manner of topics from star formation, planet formation, black holes, GR, supernova, who am I missing? A galaxy evolution. We've got a whole lot of cool stuff going on. And there's a lot of observers to talk to as well. It's a big group, one of the biggest groups outside the CFA in the country, I would say. So come check us out. All right, I will thank you for your attention and take any questions.
Thank you, Kaitlin. That's great.
To go back to your first puzzle, what is the stellar density in the places where these binaries are forming and evolving?
Not high enough to get a lot of random binary-binary interactions. You got to go to globular clusters. Even the core of Orion, which is like 10 to the 4 stars per cubic parsec, that's sort of marginal where you expect to get a lot of close interactions. I think that the number for the typical star-forming cluster, this is some work Fred Adams did a few years ago, is that you probably expect one encounter within a few hundred AU. So it's hard to get a lot of help in hardening binaries the way you would in a globular cluster, if that's what you're
Yeah, I was
thinking
sort of
about.
going to that. In globulars you do have tidal captures.
Yeah.
You do have doubles and triples doing all kinds of things to each other, forming systems that we see today as special systems. So I was kind of hoping that there might be an analog here.
Yeah, I think on average the stellar densities are just too low.
Even early on. So
Even
how does
early
the density
on.
evolve with time?
I mean, they get less dense with time, for sure, right? As the gas goes away, the clusters become unbound, but you still don't end up with globular cluster densities in general if we compare to the star-forming regions in the Milky Way. Alyssa could probably give you a better number on that than I can.
That seems reasonable.
Okay, so not very high.
Charlie, if you want to be exact.
No, it's right.
Okay. We agree.
Great. So, bottom line is if you start out with things that are already bound in high multiplicity, you're going to do a lot better.
Thank you.
Good, John.
Should New Horizons have seen your debris particles?
No, probably not, right? They're not going to necessarily be next door, right? The
You'll have
collisional
to be
family doesn't
nearby
have to
or
be, it's in the same orbit, it should have a low relative velocity, but it doesn't have to be adjacent to it.
Okay.
Could have been extremely unlucky to hit one.
It could have been extremely unlucky to get hit, and actually, people spent a lot of time looking with HST to make sure that New Horizons wasn't going to smack into anything. Because that would be bad, right? You have a meter, it's crazy, right? It's like a meter-sized body, is moving at, bullet speeds and would just have totally obliterated the mission. So they had this whole thing where they turned on the camera just before they went in and, made sure that there was nothing there. They had done all these drills, actually, where they, sequestered all of the New Horizons teams in these rooms for, 72 hours, and then they simulated how they would recalculate the trajectory if they had seen debris. I wasn't part of that.
I have a question, but I'm trying to keep someone else. Okay, I'll ask the question. Can you put one of those blue B5 pictures back up?
Yeah.
So this B5 system that Kaitlin showed you a few people here, so this is one of my favorite systems. And when we did this paper, there's another paper that we haven't written yet, and I won't talk about why not. But anyway, there's this huge...
Don't tell me it's wrong. Don't tell me it's wrong.
No, it's not wrong. No. There's this huge filament, that goes to parsec scale that actually connects this whole thing. And as you know, in this paper, it says that there's a time scale of only 40,000 years, for this little fragmentation or whatever you want to call it that happened. And so we actually don't think that it's really fragmentation, that there was ever a blob there, but that instead it's more like Stella's picture, which you had a few slides back, where there's all this filamentary crap. And that the reason that the large-scale filament still looks like the small-scale thing is because it just hasn't had time to change. So my question is, how far could that go? In other words, could you have that kind of filamentary, kind of almost accretion stream stuff going into the scales of the next picture where you want some perturbation, but you sort of go to the plain dynamical modeling and forget about the gas. But what if there actually were still these kind of gas streams on much finer scales than this?
Yeah, so we've looked at that. We've done simulations of the disk phase where we start with turbulent initial conditions and you have sort of filamentary structures feeding the disk.
Yeah.
And Anna showed some nice pictures of that in her talk earlier today. And what you see is that the main effect is that you end up shifting the angular momentum vector of the disk over time so it can wobble a little bit.
Yeah.
It can make the disks a little bit smaller. So it might, in some ways, inhibit instability if you make the disk too small, but then it can contribute it because you're kind of hammering hard on one side of the disk rather than the other. So it has some effect, but I don't think it changes the qualitative picture that if you rain material on quickly enough, you can still cause the fragmentation to happen.
Right.
Well,
we were very surprised. This was supposed to have no structure.
Yes.
But anyway, never mind.
That's true of
A
all
whole
the
other
disk
story,
pictures.
right? So I just, what I'm thinking is that there's probably even more structure hidden in that picture.
There might, yes, and that's what ALMA has showed us. Every time we look at higher resolution, there's
Right.
more and more substructure. I hope there's not too many more objects in that disk, because then I don't know what I'm
Then
doing.
your beautiful picture.
Then my
doesn't
beautiful
match
picture
it.
doesn't match, and I want to hold on to that for at least like a year. So.
I think you just say we can crack. She said, yeah, a year. A year.
Are there any polarization measurements of the beam
This
velocity?
one?
Yeah.
We've proposed that to ALMA several times. Anyone on the ALMA task team? Kill that? Let's put it back. And
When you're talking about the one-sided disks, you were using a 5 Jupiter mass planet, but that's not even a very big object when you could have a 100 Jupiter mass brown dwarf, right?
You could, but then you'd see it in the disk, right? So this is the problem. That's why, and in fact, even 5 Jupiter masses now, our direct imaging surveys for exoplanets have gotten so good that at the separations of some of these asymmetries, we probably would have seen a young 5 Jupiter mass object because they're very bright at that phase because they're either still accreting. There's been some detections of these objects in like H alpha as well. And to our best ability to detect, there's not a whole lot of things that are a few Jupiter masses at separations of several tens to hundreds of AU from stars. They're just not there. So in fact, thinking it was 5 Jupiter masses is going in the wrong direction. We probably should make it 1 Jupiter mass, and then all the problems I talked about get even worse, where it's really hard to make these structures without some pretty, fine-tuning of the model.
Does the failure to see those, is that starting to worry you?
Is it starting to worry me? No, I'm sure we'll come up with some other creative wrong explanation.
Kaitlin wins the Humorous Honesty Prize.
So if I remember right, one of the results from Kepler is that circumbinary planets are pretty much missing around the shortest of period binaries. So does that just remain a puzzle on top of the puzzle of how these things form? Or is there...
Well, I'd say that's an unsurprising conclusion because I think, and people have now shown this, that if the very closest binaries were made by Kozai oscillations, it's very hard to maintain a planet around that system in the first place. If you manage to have the planet there form and then have the oscillations start, then the planet will end up getting either kicked to high inclinations or ejected from the system entirely. And if you wanted to have the binary form first, the problem is that the process of undergoing the oscillations probably would have gotten rid of that disk of material around it because you would have been causing the eccentricity to grow and shrink and grow and shrink. So I think it might be hard to form planets after the fact as well. But what I would argue is that what I think it tells us is that there must be some other part of the story to make some of these close binaries that's giving us both these very, very short period things and these slightly longer period things with planets that doesn't involve Kozai-Leonov oscillations, that allows us to keep that disk.
Yeah.
Now, one thing, I'm wondering in these regions, now going to the question of the asymmetries, are they perhaps dense with small objects like planets? I mean, do you need to rely on something that's actually part of your system to give you the initial asymmetry? Or could you have a flyby, for example, that would give you some type of an asymmetry?
I think it's hard to get something that would be long-lived enough that we would expect to see so many from just a flyby. And there's some evidence that, there's good evidence from the observations that those asymmetries are in fact pressure bumps of some kind, because we can look and see how the particles are concentrated as a function of size by probing different wavelengths with ALMA. And you see the trend that you would expect where the smaller particles are more concentrated in the center and the larger things are a little bit further out, which is what you'd expect based on the drag time scales.
So it's intrinsic.
So it looks like it looks like you have a pressure maximum in the gas that is trapping dust rings. That part seems pretty good. It's just what caused that is not totally clear. Whether or not it's a vortex, it's very hard to measure the velocities. So, yeah. I think Sean had to leave, but you should ask him. He may have a new hypothesis that I haven't heard.
Great. Okay. Well, a few of us are going to dinner, and there's 1 or 2 more spots possibly. And so, if you'd like to join and you haven't already said so, please tell me afterwards. And if you are coming, please just come up here afterwards. So, thank you very much, and thank you.